Well, g'day flatties and globe defenders, it's Critical Think from Down Under. Just a few hours ago, Ranty claimed that this sinking experiment crushes the globe rhetoric. Let's just listen to what he says about this.
Well, what's the answer to that? Well, the answer to that is this, the density gradient, and this, nothing's changed apart from the tin has dropped in its position. Game over, globies.
Game over. Well, you heard what he says. Nothing's changed except that the tin has dropped. Well, let's look at this. First of all, there is no picture of the paint primer when there is no sugar in the water. He's comparing a tin viewed through a fish tank with sugar water with a tin viewed through sugar water in a fish tank. Now, there is a little bit more sugar water in the fish tank to the right, but where is the picture, the control, where is the picture of the paint primer when there's no sugar water? It's not there. How can we properly compare it if there's no control? But don't worry, we've measured the height of the water in the fish tank, a very important metric. And here's another thing. These photos are the photos he compared, this one and this one. Now you'll notice that they're taken 7 minutes apart. 7 minutes. That's hardly enough time to let the sugar settle in the solution. You're not going to get a stable gradient with just 7 minutes. But not only that, this first picture is taken without a stable gradient. And notice the lack of clarity in these photos. Now, where's Travis when you need him? Travis, why aren't you here berating Ranty there about the clarity of these photos and the out of focus? Oh, goodness me, you're slipping up there, Travis. So, we have these photos and look at this. Here's another thing. One of the most important things is this measurement that was supposed to be on the back wall there. But look at it. Come on, Ranty. Strap your tape to the wall so that it doesn't have all these bows and kinks in it. If you want an accurate measurement, we want to see the undistorted measurement. But not only that, look at that. The marks on the wall show that without the sugar water, the laser is higher. So when he shines a laser through the tank, the laser beam gets bent downwards. So that would produce looming. But anyway, it's great that it's okay now to shine a laser through a fish tank. So now we'd be able to show you this, where somebody else has shone a laser through the fish tank and demonstrated looming over a curve. Now, I remember it wasn't so long ago that you berated me for using water in refraction experiments, but here you are, you're using water now and it's okay now, so I can show you this. If it's okay for flat earthers, it's okay for globers.
All the way down, and you can see it's being compressed. Up again, it's back to normal. Go down.
So there you go. Looming over a curve, using a fish tank, just like you're using. Right, so let's see if your comparison passes the blink test, the Critical Think blink test. Did you see that? Maybe that was no good. Let's just make it like this. So here's a couple of things to notice in this blink test. The can is stretched and then the can is compressed. It's not actually sinking, it's compressing. But not only that, there's a dot up the top that moves up. That's in a loomed up. And not only that, this bench top here, or whatever it is, moves up. So although the top of the can might move down, the bottom is moving up. The garage door is moving up. The top of the picture is moving up. And goodness me, I don't know what the tape measure's doing, but it's stretching and doing all kinds of weird things. So really, your gradient's not linear. So not much of a test there, is it? What are you going to be able to tell from that? Nothing much. So in this comparison that Ranty shows, you can easily tell that the can on the left is stretched. So this is why you need to show the can through the tank with no sugar in the water, so that we can do a proper comparison. You can claim it's sinking, but that doesn't mean it's sinking. And in fact, there's more parts in that comparison that were looming rather than sinking. So I've taken this label off the paint can on the left, blown it up, compared to the one on the right. You can see the one on the left is stretched. So how can you say? You cannot say for sure that that one is sinking, because this one on the left is stretched. So just remember, Ranty, when you asked for proof of looming, you wanted to see something that is lifted up from beyond the curve in its entirety. Now, you wanted to be able to see the target without any distortion and not be able to tell the difference between the image of the target and what you see. So, why does the same criteria not apply to your own evidence? One of those images is stretched, the other one isn't. We are able to tell the difference between those two. So next time when you try this experiment, you should try it again, because it's a great experiment, but unfortunately poorly executed. So take a picture first with no sugar in the water. Take a picture through the tank with no sugar in the water. Then add the sugar solution. Wait for the gradient to stabilise, and then take another picture. And no cherry picking. You think that you've proved that things sink over a distance, and this is why the Miles Davis observation can work on a flat Earth. Well, if you think that, then I've got something for you to consider here. I've got something that I want an explanation for. I have two pictures here, the same ship on the same day, a few minutes apart. The first one is at 15 metres in height, and the second one is less than 300 millimetres from the surface of the water. So let's play this. Now, this is a blink test. So, for all you flat earthers who are so-called refraction experts, can you explain why is the water higher? Why does the water rise up when the observation height gets lower? If things were supposed to sink in the distance, how can the water get higher? Simple question. Do you have a simple answer?